Hello, welcome to lesson 2. We will pick up where we left off on counting and then lead into the binomial and multinomial theorems. Okay, so the question here from the text we're looking at, how many different linear arrangements are there of the letters A, B, C, D, E, F if we're requiring A and B to be next to each other? Now, note here that it's implied that in the linear arrangement, the order does matter, repeats are not allowed. So they're asking for the number of different arrangements here where A and B are next to each other. Now, the order does matter, so we will do this for AB, and then we will have to also do this for BA, which will just amount to doubling. So the idea here is that we have to place A and B next to each other, and basically the other remaining 4 letters from the 6 total will go in the remaining slots. And so the count to fill in those extra 4 blanks will be 4 factorial. We have 4 choices for the first slot. We can't use the AB. So you have 4 choices followed by 3, 2, 1. So it's 4 factorial for the remaining 4 slots. So then the only question is, how many locations are there for the AB? And so basically here, we can start with AB all the way down to ending with AB. We cannot end with A in this order because we have A first, then B. And so that leads to 5 different possibilities for placing the block AB. So the total here would be 5 choices for where to place AB times 4 factorial for the remaining 4, which is the same as just 5 factorial. So one way to think of this problem is to think of AB as one letter. And so what we've done is reduce the problem to arranging 5 letters instead of 4, and you get 5 factorial. Now we have to double because we can reverse, and we have to redo this with BA. It's going to be the exact same count. So the final answer is going to be 2 times 5 factorial, 2 times 120, which is 240. But there is a faster way to do this. My apologies here. That is basically the fastest way. There's going to be the next in an upcoming problem. There's going to be a shortcut, but the fastest way to do this problem is to use the fact that we're basically combining AB into a single letter, leaving us with 5 letters for 5 factorial. We double because we can use AB or BA. So it's 2 times 5 factorial, which is 240. All right, now part B. How many different arrangements are there resetting to just that A just has to be before B, not necessarily next to it, just before B. A is placed before B. So this one could get messy here if we do this the long way. If we place A first, then we would have any of the remaining slots will have B coming after, and A is before B would be satisfied. Now, if A is placed second, then we cannot place B in front, and so B would have to go in one of the 4 slots after A, and so on. But there's a much faster way to do this problem. The chance of the number of ways that A is before B is the same as the number of ways that B is before A. We can't have them in the same slot. So it's an equal count. A is before B, B is before A. So we just have to divide the grand total by 2. We have 6 letters here. So there are 6 factorial arrangements, which is 720. We just divide that by 2 and get 360 for the final answer. So again, you can do it out in cases and total it up. but it's going to be a lot quicker to view this as a total of 6 factorial ways to list this out. We have order matters, repeats do not allow are not allowed. So it's a permutation, which is 720. 6 factorial 720 divided by 2. Half of them would have A in front of B, half of them would have B in front of A, which leaves us with 360 possibilities. Part C, A is before B and B is before C. So we can look at an arrangement here of just those 3 letters, A, B, C, and we see if we do all the possible listings of A, B, C, there's only one way to satisfy this condition, A, B, C. A has to be before B, and B is before C. So out of the 6 here total ways to scramble A, B, C, there's only one way to satisfy this condition. So building off of that, we're going to say that 1/6 of the total will have the ABC in the correct order to what the question is asking. So the answer will be the grand total divided by 6. 720 divided by 6 is 120. Again, this is counting it out the long way, but the original method here is going to be a lot faster. Part D, A is before B and C is before D. So from part B, we know to get A is before B, we took the grand total and divided by 2, 720 divided by 720 divided by 2 was 360. Now we also we need C to come ahead of D. And so again, we're just going to divide by 2. Half of these will have C before D versus D before C. So we divide 360 by 2 again, and we get 180. I'm going to leave part E for you to work on. Part F, E is not last in line. Now, in this situation, we'd have a lot of possibilities here because E could go anywhere in the first 5 slots. It's going to be easier to count all the ways this doesn't happen. How many ways are there for E to be last? Count that up and then subtract from the total. So we're looking at the opposite or the complement point of view, which is how many ways is E last, and then subtract from the total. So the total is 720. If E is last, we're left with 5 factorial arrangements because there are 5 slots here. The 6th slot is filled in with E. There are 5 slots available for the remaining letters, so that's 5 factorial. So the final answer would be the grand total, 720 minus 5 factorial minus 120, which is 600. So again, we counted the ways that E could be last. We put E in the last slot. There's 5 factorial ways for the other letters. So there's 120 ways for E to be last, but we don't want that to happen. We want the opposite of that. So we do the total 720 minus 120 to get 600. Now, if you want to do this in a more direct fashion here, there are 5 places to put E if you want to avoid the last slot. So you have 5 possibilities for placing the E. And then once E is placed, you have to fill in the 5 other slots with the remaining letters, which is 5 factorial. 5 times 5 factorial, 5 times 120 ends at 600. All right, now we'll take a look at some semi-new material here. We will be using some of these counting techniques that we saw in lesson 1 in this part as well. The binomial theorem here, raising a binomial x plus y to a power here, in this case the third power, is repeated multiplication. x plus y times itself 3 times. Now, we could think of this here in a counting situation. We have two terms in each parentheses, and each product, each expression in x plus y cubed will come from creating a product by selecting one of the two terms in each expression and multiplying together. So we have two choices for the first parentheses, two for the second, and two for the third. Leaves us with 2 times 2 times 2, or 8 possibilities. So there's one possibility is to use all the x's up, and that would give us an x cubed. Now, there are three ways to get x squared y. We can do xx and y last, xyx, or yxx. So there's three ways to get x squared y. There are three ways to get xy that should be squared. All right, my apologies here. So we have that corrected. So it's going to be x to the third, then there's 3x squared y, and then 3xy squared, because you can do xyy, you can do yxy, and you can do yyx. So there's three ways to do that, and then there's one way to do y to the third. You have to select y, and so you get y cubed. Now these coefficients here, 1, 3, 3, 1, which add up to the 8 terms here, those are actually combinations. 3 choose 0, representing we selected 0 of the y's, and then 3 choose 1, 3 choose 2, 3 choose 3. Remember, alternate notation for NCR is to use the parentheses. If we're squaring x plus y, we're going to get 1x squared plus 2xy plus 1y squared. Corresponding coefficients are 2 choose 0, 2 choose 1, and 2 choose 2. So these coefficients can be found using Pascal's triangle. We start out with a 1, and then we're basically adding the terms directly above the value to get the next row. So we can think of the empty value as 0, so we get 1, 1, and then the third row we get a 1, and then we get a 2, since this entry here is below 1 plus 1, and then the last entry is going to be 1, because you could think of it as 1 plus 0. All right, then we go to the fourth row. It's 1, then 1 plus 2 is 3, 2 plus 1 is 3, and then a 1. So it's 1, 3, 3, 1. The next line, we have 1, and then 1 plus 3 is 4. 3 plus 3 makes 6. 3 and 1, 4, and then bring down the 1. Finally, we have 1. 1, 4 is 5. 4, 6, 10. 6, 4 is 10. 4, 1 is 5, and bring down the 1. So those generate the coefficients for x plus y to the nth power. So the top row is corresponding to power 0, just a single 1. Then the second row is power 1. We get coefficients of 1 and 1. Third row, we get a squared plus 2ab plus b squared, corresponding to the 1, 2, 1, and so on. Notice in the expansion, the powers on a and b add up to the original exponent, in this case 5, right? We have 5, and then 4, 1, 3, 2, 2, 3, 1, 4, and 5. Notice that the powers on A decrease, 5, 4, 3, 2, 1, 0. Powers on B increase, 0, 1, 2, 3, 4, 5. And so we have a general formula here for expanding x plus y to the nth power. Summation k equals 0 to n choose k, x to the k, y to the n minus k. Again, the exponents on x and y will total up to n, and we can use the alternate notation for a combination. So a standard question in this setup is to find a specific coefficient. So if we're working with x plus y to the eighth power and we want to find the coefficient of x to the 6 y squared, the combination term we're looking for is 8c6 or 8c2. You want to convince yourself that those things are the same. We have the symmetry of the triangle, which can explain that. Another way to think of this, every time you select two objects from a set of 8, you're leaving behind 6. So there will be a matching count for removing 6. It's this same count for removing 2. Now, this problem is a little bit trickier because the expressions we have in our binomial already have coefficients. So we have to keep track of those as well as the standard coefficients from the expansion in the triangle. So we have a 10th power situation, finding the coefficient of x to the 7th, y to the 3rd. So we're going to have our combination term, 10 choose 7 or 10 choose 3, in addition to these coefficients of 2 and 3 here. So you have to keep track of that. 2x, so 2 is going to be the 7th, and negative 3 is going to be raised to the 3rd power. So our coefficient will be 10 choose 7 times 2 to the 7th times negative 3 cubed. If we have 2a plus b to the 4th power, the coefficients will be 1, 4, 6, 4, 1 for the 4th power. And the powers on the first term will decrease, 2a to the 4th, 3, 2, 1, 0. And the powers on b increase, 0, 1, 2, 3, 4. So the full expansion will be 1 times 2 to the 4th, which is 16, a to the 4th. 4 times 2 cubed is 8, 32, a cubed b. 6 times 4 is 24, a squared b squared. 4 times 2 is 8, ab cubed, and then 1 copy of b to the 4th. So that's what happens if we have a coefficient within our binomial. If you have powers within the binomial, then that's going to really make things a lot messier. You'll have the sum going beyond n in that case. Multinomial coefficient. So now we have more than two terms in our expression. If we're squaring the trinomial a plus b plus c, it's a plus b plus c times itself. We have 3 terms in each parentheses for a total of 9 possibilities. And so the coefficients here, different from Pascal's triangle, it's 1, 2, 2, 1, 2, 1. And so we still have a situation where the powers on the variables will add up to n. In this case, all the powers on each term, combining the variables, it's all 2. And so the formula for the coefficients here is going to look very similar to what we had for the permutations with duplicates. N factorial for the total, and then divided by the duplications here. So looking at this example, if we want to find the coefficient of AC, the power on A is 1. So we have one occurrence of A, no occurrences, 0 occurrences of B, 1 occurrence of C. So we really don't have any repeats here, but we can plug into the formula. The total here is 2, so the numerator is 2 factorial. Denominator is 1 factorial, 0 factorial, 1 factorial. And so we just end up with a 2. Which is what we had in our expansion here. We were trying to find the coefficient of AC, which was 2. What's the coefficient of C squared? Well, we saw from above that the coefficient of C squared is 1. So plugging into the formula, we should get a 1 out here. Let's take a look. So in this case here, There's no A term, there's no B term, so there's 0 of those, and then there's 2 copies of C. The exponent on C is 2. So the total n is 2 factorial divided by the 2 C's divided by 2 factorial leaves us with a 1. So if we were trying to split up n objects into sizes n1, n2, n3, the total adds up to n. We can think of it as selecting n1 from the original n2 from the leftover, and then n3 from the leftover portion that remains. But the amount that remains is just n3 because the total is n, so it ends up just being n3. Choose n3. So to recap here, n choose k is n factorial over n minus k factorial times k factorial, which is a combination. So n choose n1 is n factorial over n1 factorial times n minus n1 factorial. Then we're doing the remaining amount, n minus n1 choose n2. So it's n minus n1 factorial divided by n2 factorial times n minus n1 minus n2 factorial. And then again, n3 choose n3. Those numbers are the same. There's only one way to do that. And then we get some cancellation here. The n minus n1 factorial cancels out. And so we're left with an n factorial upstairs, n1 factorial, n2 factorial. And this expression here is n3 factorial. And so it becomes the formula for permutations with duplicates. Let me just make this a little bit bigger here. Sorry about that. So just to recap here, when we do this out, n3 choose n3 is 1. If you're taking all the objects, there's only one way to do that. We have n choose n1, which is n factorial, n1 factorial, and minus n1 factorial. Now, the second expression there, we're selecting from the remaining amount. So our total now is n minus n1. So we have that factorial upstairs. We're selecting n2, so we have n2 factorial downstairs. And then the difference, n minus n1 minus n2 factorial, but that's just n3. So the net result of all this, and I know it's very messy, the net result here is we have our permutation with duplicates formula here. And so this is the generalized formula for a multinomial going beyond the binomial situation. So if we're dealing with the 4 terms here, a plus b plus c plus d to the 7th power, and we want to find the coefficient of a squared b cubed cd, exponents there 2, 3, 1, 1, add up to 7. We do 7 factorial divided by 2 factorial, 3 factorial, 1 factorial, 1 factorial. 2 factorial is 2, 3 factorial is 6, so downstairs is 12. 7 factorial is 5,040, so the coefficient happens to be 420 after division. Now, this is a binomial situation, so you could just use the shortcut formula or the same one here. It's going to be 10 factorial divided by 6 factorial, 4 factorial. So again, you can think of this as permutation with duplicates here. Or you could use the combination formula. How many ways can we split a 12-person jury into subgroups of sizes 5, 4, and 3? So this is in the same context of above. We have a total here, 5 plus 4 plus 3 does equal 12. We're splitting up the 12 people into sizes 5, 4, and 3. So it amounts to a count of a permutation with repeats. And so we get 12 factorial over 5 factorial, 4 factorial, 3 factorial. if we do this in a more direct way, without, well, got to be careful by, let's say, the definitional way as opposed to the shortcut, we're taking 5 out of 12, leaving us 7 left over. We're gonna select 4 from those 7, and then 3 from 3, which is only one way to do that. All right, coming back to the harder counting situation that we skipped in lesson 1, unordered with repeats. We'll take a look at that here. We're going to select 4 out of these 6 letters here. The order doesn't matter, but repeats are allowed. We could select 4 copies of B, or 2 copies of D, 2 copies of E, and 2 copies of F. So we're allowed to take repeats here, but the order doesn't matter. So we have this picture here, which I think makes this situation a little bit easier. So the idea here is basically how many. We're going to make 4 selections denoted by the 4 circles. And then the question is, how many A's, B's, C's, D, E, and F are we going to select? So there's 6 different types to choose from. We use 5 vertical lines here to split this up into 6 pieces. So we have an A section here to the left, then B, C, D, E, and F. So 5 lines to denote 6 letters. The 4 circles are the selections we're going to make. So in this particular context here, this setup is referring to not selecting any A's, 1 copy of B, no 0 C's, 1 D, 1 E, and 1 F. So this listing here of lines and circles is corresponding to selecting B, D, E, F. And so the idea here is that the total number of ways to select 4 out of these 6, order doesn't matter, repeats allowed, is the number of ways to arrange these 5 lines and 4 circles. Let's take a look at just another possibility before we look at the count here. So if we arrange in this order, where putting in our 5 lines and 4 circles. So we have one circle at the very left. That's 1 copy of A. Now there's a blank in here, so that's 0 B's. Now we have 2 circles in a row. So that corresponds to 2 copies of C, and then 1 copy of D. No E's and no F's. So this corresponds to the selection of A, C, C, D. So again, 5 lines gives us 6 categories: A, B, C, D, E, and F. So this amounts to now, hopefully, if you can believe this amounts to counting the number of ways to arrange 4 circles and 5 lines. And so we think of this as a permutation with duplicates. We have 5 lines and 4 circles. So we have 9 total objects, so 9 factorial upstairs. Downstairs, we have the repetitions. We have 5 lines, so we're going to have a 5 factorial, and we have 4 circles. We're going to have a 4 factorial. And so it ends up being 9C4, 9 factorial over 5 factorial, 4 factorial for the 5 lines and 4 circles. So the overall formula here, we had it in the chart last time, but the overall formula is the following. We're going to add up 4 plus 6 is 10 minus 1, because we need 1 less line to make 6 categories. So it's 4 plus 6 is 10 minus 1 is 9. Choose 4 for the total for this count. Now, again, some of these counts are a little bit messy, especially this unordered with repeats, and even some of the counting problems at the beginning. again, moving forward for the rest of the course, these problems are interesting, but moving forward for the rest of the course, we're going to be working with, for the most part, the simpler combination permutation counts as we move forward into probability here. If you have any questions, as always, please feel free to email.